So let's pick up from there. So we've opened, let's say we open our refrigerator, freezer unit inside a room, well insulated, well sealed. As we said, initially you're going to see a drop in the average temperature in the room, or I guess just the room temperature. But if you take an average of the temperature within the freezer and the refrigerator and then average that with the temperature of the outside air, and you average up all of that kind of temperature, if you will, you're going to notice that it's going to be about the same before and after. The average is going to be about the same before and after you open these units up. The total energy is still going to be the same there. But if you allow this thing to run over a long enough period of time, you're just adding more and more energy into this system. Eventually, we're going to see an increase in temperature within the room. Okay? So, a couple of things here. Sometimes you'll see just a generic capital E, right? A generic capital E referring to a sum of energies, various kinds of energies. There's different kinds of energies, and if we add up different kinds of energies together, we don't know what kind of energy they are, so we'll just use a generic E. Now, energy per unit mass, so if I take this total energy and I divide it by the amount of mass, then I get this quantity that is energy per unit mass. It's specific energy. And notice here this is a lowercase variable. So anytime I have something that's per unit mass, if it's per unit mass and it now becomes what we call an intensive property, like the specific volume, then that is we use a lowercase variable in that case. So the capital variable for the extensive property, the lowercase variable for the intensive property, just like we had with volume earlier. Right? We said total volume, capital V. Specific volume, that's volume per unit mass, that's a lowercase v. And that is a common, common nomenclature we'll use in many of the thermal science courses like thermodynamics, where we use a capital letter to represent the total quantity and a lowercase variable to represent the same quantity per unit mass. Okay? So a couple of quantities here, a couple of types of energy that you are probably familiar with, hopefully you're familiar with because you've had Physics 1, kinetic energy and potential energy. These are what we call macroscopic energies, right? Macroscopic energies. They depend on some outside reference to be measured. So one of my favorite questions, are you moving right now? Right? Are you moving right now? And it's okay, take a guess. Some of you maybe are saying yes, and some of you are maybe saying no, and the truth is you're technically both correct. The proper response to are we moving right now, the proper response is with reference to what? Relative to what? Right? How are you measuring me? If you're measuring me relative to the sun's position, yes, I'm moving very, very quickly. So are you. Relative to your chair or your computer screen, maybe you're not moving very fast. So maybe relative to those objects, your velocity is zero. Your change in elevation is zero. So these are macroscopic energies. They depend on some reference, some outside measurement. As we mentioned, these are total amounts. If I use a lowercase ke, that is simply v squared over 2. So I divide by mass. Same thing with lowercase p, lowercase e, that is simply g times h divided by mass. So per unit mass, we'll use lowercase variables to describe those. Those are macroscopic energies. This is microscopic energy. Microscopic energy is dependent on something else. It's dependent on the molecules, the particles, the motion, and the energy level of those particles. So this is energy at essentially the atomic level or even subatomic level, depending on what you're dealing with. the internal energy will represent as U. And that's the idea. We're going to take the kinetic energy and the chemical energy and the spinning energy and the oscillation energy of every single atom or molecule and add it up. We're going to take our scanning electron microscope, and we're going to measure the motion of every single particle within the system and try to measure its energy. And that's just silly. We cannot do that. we cannot do that. However, what we can do is we can measure it, or we can estimate it using other properties like temperature, phase, pressure, volume. So we can measure this, or we can estimate the internal energy based on other properties. We can estimate it based on other properties that we can actually measure for our system. Temperature, pressure, and volume being the main ones. Now, this is internal energy. This is specific. Internal energy is lowercase u. Total internal energy, as I said, have you a sheet where you see, you can kind of make a note of how I'm going to write these. So total internal energy, I've learned to just kind of put these hats on top of my u, and that draw it larger than my lowercase variables. So how do you know if it's a u or a v? Well, if I'm drawing it, I'm going to put a little extra tail on this u. And if it's got the tail, if it looks like a u but it's got the tail on it, that means it's a lowercase u, not a capital U. Right? So lowercase u is big U per unit mass. Okay? So like I said, keep track of, if you haven't already started this, you might want to pause and write these down. It's kind of important. You're going to continue to see these. And then just have that on a separate sheet of notes. That's easy to grab. Okay? All right. So again, internal energy, microscopic energy, dependent on the energy within the particles. Okay? Can't really measure it directly. We're going to measure it based off of other properties. Now, so this would be the energy of a system. Right, so this is what types of energy can the system have. Right, this is energy of a system. Sorry, it's kind of hard to write with just my fingertip there. System. This is the energy of a system. All right? So what types of energy can a system have? Well, a system can have its own internal energy. It can have its own kinetic energy. It can have its own potential energy. And we can find those based off of quantities that we can feasibly measure. Right? The speed finds kinetic energy, the elevation finds potential energy, and the other properties. In Chapter 3, we're going to talk about how do you find the U value, how do you measure the internal energy or estimate the internal energy of the system. Okay? Now, if I divide each of these by mass, you can see what happens there. I get lowercase parameters there. Right? So energy, total energy for my system, is equal to a lowercase u plus v squared over 2 plus gz. That would be the total energy of this is the specific energy of the system. Okay. Now, if you don't have this written down yet, pause. I'm going to go ahead and move on to the next slide. Okay. Now, if I'm dealing with control volumes, because I've got mass flowing through it, it's not as a lot of times we don't think about what's the total mass of the control volume. We think about what is the rate at which mass moves through it. What is the rate at which it's changing? And what we do is we put a dot above those parameters. Okay? So let's talk about rates here. So mass flow rate. This is m with a dot above. If I put a dot above a variable, that means that variable is being measured per unit time. It is a rate. So m with a dot above it is mass per unit time. This is red, m dot. That's how we'll say it. This is m dot. It refers to the mass flow rate, or the mass per unit time. The volume or volumetric flow rate, that is volume. That's big V with a cross on it with a dot above it. That is volume per unit time. Again, we'll read this as V dot, is how we'll read that. Okay, now how do we find m dot? There's a bunch of ways we can find m dot. Okay, so one of the main ways we would find m dot, notice this is volume per unit time, and here this is mass per unit time. So what we can do is, if I've got something that is mass per unit volume, like density, that's mass per unit volume, multiply that by something that is volume per unit time. All right, so if I take mass per volume times volume per time, I get mass per time. So density times V dot gives me m dot. Now, if I happen to be given V dot, that's fine. If I don't know V dot, some other things I might be able to find. If I've got some kind of a flow rate measurement, some device that measures the flow rate, what it's probably going to measure is the speed of flow, right? So there's a couple ways I can find V dot. If I can measure the speed of flow, now that's not volume, right? So if we think about how do we get volume, how would we get volume? And I guess I might ask, how do you get the volume of a box? Just kind of change gears just a little bit. Think about that. How do I find the volume of a box? Base times width times height, right? Or length times width times height. What you're doing there is you're finding the area of one face, and you're multiplying by a third dimension, right? If you find the volume of a cylinder, that's like pi r squared h, right? Pi r squared h. Sorry, I had a weird alarm there. Pi r squared h is the volume of a cylinder. That's the area of a circle multiplied by a third dimension. So anytime I've got an area multiplied by a third dimension, that's going to give me a volume, right? So what if I've got, here I want volume per time. So if I know if I've got area times length gives me a volume, what do you think happens if I take an area times something that is length per time? So I've got area times length per time. Well, area times length gives me volume. So area times length per time gives me volume per time. Right? So if I take density times the, let's say I've got some kind of conduit, and I've got fluid coming out of that. Well, this fluid's going to come out at some average speed, and I'm going to have a cross section area that we'll just call A. So if I take the average speed at which the molecules or particles are coming through this conduit, multiplied by the cross-sectional area of that conduit, that product gives me volume per time. That's V dot. Multiplied by rho, and that gives me m dot. And by the way, remember our good friend specific volume is the reciprocal of density. Remember the sheet I told you guys to keep handy, this guy, right? Why do you need this? Well, because you need some way to know the difference between which V am I talking about. Am I talking about volume, speed, or specific volume? Because all three are going to show up in some of these equations. All right, we'll pick up there on the next video.